Hello. In this video, we're going to talk about the semi-log graph paper, which allows us to find a better exponential than Excel, at least in some cases. So let's take a look at an example. Here we have a data set for X and Y that we plotted. And as you can see, it appears to have an exponential trend to it. And so when we ask Excel to find the regression line for it, it gives us a formula. And sure enough, the R-square value is really great, 0.996, fits the data fairly well, and it gives an SSE of about 11,000. And so our question is, can we do better than that using semi-log graph paper? So let's check it out. So how does semi-log graph paper work? Well, recall we're trying to find the model for something of the form y equals a times e to the kx. Or maybe what's better, a times 10 to the bx. Because it's easier to use logarithmic paper based on base 10 than base e. So if we think about it like this, then I can take the logarithm of both sides and then simplify. And so if we do that, we get the log of y equals the log of a plus log of 10 to the bx. And we know the log of 10 is just 1, so this simplifies a little more to the log of y equals the log of a plus bx. And the good news is we have a linear function if we replace log y with a new variable called capital Y, the transformed version of y. In that case, we have capital Y equals bx plus log a, which is definitely a linear relationship. So this is similar to what we saw in the last video with log paper. The difference is that we only had to transform one variable, y, but not x. So the x values are not transformed. The other consequence of that is that before we had a one-axis for the x variables, but in this case, the traditional zero axis for the y-axis is fine. So it's okay to use the zero axis for the y-axis. So we'll see that in action here in a minute. But these are the two main things that are going to be different on our semi-log graph paper. Otherwise, the things that we talked about in the last video will still apply. So let's try it out with that example we just looked at. So here's our semi-log graph paper, and you can see that on the x-axis, the tick marks are equally spaced, so it hasn't been transformed, but we have three cycles of logarithmic tick marks on the y-axis. So here's our data set, and let's see if we can plot our points. The first thing is we need to set up our axis in each direction. And the x values, notice, range from 4 to 17, so I need to plot my values accordingly. Recall, I really want to have 0 for my y-axis to correspond to that. And then we'll have 1, 2, 3, 4, 5, 10, 15, and then 20. So the good news is all my data fits on the x-axis. And then for the y-axis, I have 3 orders of magnitude. So that means I can start here at 1, go to 10, go to 100, and go to 1,000. So my 3 cycles correspond to my 3 orders of magnitude. So now let's actually plot some points. So 4, 8. So here's 4, and then 8 is going to correspond to right here. So I can put a point right there. 7, 13, 7 is there. And then 13, notice between 10 and 20, this first tick mark is a fourth of the way, so that's 12.5. So 13 is just going to be a little bit above that. 9, 20, so here's 9, and then 20 will correspond to this line right here. 13 is right here, and that corresponds to 123. Well, since this is 100, then that means this is 125. So 123 is going to be pretty close to that. So we can put a dot there. 14 is right next to it, and it's at 180. 180 is just going to be a little bit above the 175 mark. So roughly there. And then our last one, 15, 16, 17, is at 601. So 601 is basically up here. And so if I come over, so remember that was 14, 15, 16, 17. So there's our data. And if you look at the plot, it's not quite linear, but it's pretty close. So we feel relatively good about using an exponential trend line. The thing to remember is that if this had been more of a concave down sort of shape, then probably a power function or a quadratic, cubic, something like that might be worth trying. If it had been more concave up than it is, then maybe a function that increases more steeply than an exponential might be worth considering. But for the most part, we have a linear relationship. And remember, the more linear the relationship, the more likely an exponential model should fit the data well. So let's try to fit a line. So you can try your own hand at drawing a line to fit the data. But remember, just like before, the y values further up the axis are going to be worth more from an SSE perspective than the ones down here. A little error here is going to be worth hundreds, while a little error down here is worth just a unit or two. So let's draw a line. So here's the line I get. And unfortunately, the line passes through the zero axis. The y-intercept is here too low for us to be able to read it directly off the graph. If it was, then we would just read it. Now, we could probably measure it and estimate what it is, but we'll find another way of dealing with that here in a minute. So let's focus on the slope. Now, the slope is just like before. It's rise over run, but we can't use either traditional method that either you use with regular graph paper or with log paper, because this is different from either of those. So my advice is to actually focus on one cycle of the paper. And so, for example, if I pick a point here, like right here, notice that's where the 10 crosses, and that corresponds to about, I'm going to say 6.8. And then if I draw a triangle, one leg of the triangle until it crosses the next cycle. So this line crosses this cycle here. So we have our rise over our run. And this looks to be maybe a little bit left of half. So that is at, we'll call it 12.4. So 6.8 to 12.4, that means the run here is 5.6 units. So that's just like you would do the run for any graph. But the rise is what's interesting, because that's the one that's transformed. I can't just take the numbers and subtract. What I really need is the logarithmic difference. So one way of thinking about that is the log of 100 minus the log of 10. But of course, the log of 100 minus the log of 10 is just 2 minus 1 is 1. And as long as you always do a cycle, the rise will always be 1. And so that's a nice simple way of remembering it, is just pick a 2 points on your graph that correspond to one change of one cycle. Now, if you had a really shallow line, that might be trickier, but this is steep enough, we have no problem. So that means our slope is 1 over 5.6, which corresponds to our b value. Now, to find the a, we need to plug in. So just find the point that the line passes through. And actually, it looks like it passes through this last point as good as any of them. So I can just plug in. So remember, our formula is y equals a times 10 to the bx. And since we know that our data value is 17,601. Then 601 equals A times 10 to the 17 divided by 5.6. And then we can solve that for A and see what we get. You can do that with a calculator, or we can do that on Excel. And so I'm getting about 0.55. So there's our two coefficients that we need to deal with, 0.55 and 1 over 5.6. Now we can go back to Excel and see how that works out in reality. So here's our spreadsheet. Remember, the A we said was approximately 0.55, and the B was 1 divided by 5.6. I can type in my model, which was A times 10 to the B times X. We get 3, which if you go back to your plot, you can look and see if the line passes through 3 or not, which looking at our plot, that looks about right, so I'm feeling good. I can drag this down, but before, let me freeze the cells corresponding to A and B. So a dollar sign in front of 11 and 12. Drag that down. So let's see, what do we get? We get numbers that are looking pretty close to the Y values and pretty close to what I expected from my graph paper. So we can plot that just to make sure. So I insert the plot. And if we wanted to, now notice on this, if you try to change the series chart type, you might get an unsatisfying kind of straight line because it's just connecting dots in a somewhat smooth way. So instead of doing that, what I'm going to do is I'm going to add a trend line that will kind of give us hopefully the same effects. And if you want to see the equation, you can, but we already know the equation. And of course, the r squared value is not really useful in this case, so we'll take that out. So there's the equivalent. If you did want to know the form e to the kx, Excel has calculated for us. And so we can see that it does appear to be passing through the points about as well as we expected from the graph paper, although it's always hard to tell on these smaller y values. So the squared error is the better way of testing this. So the predicted minus the actual squared. Drag that down. And notice we get 153 for the SSE. So once again, we've improved our sum of squared error by a full order of magnitude. So quite a bit better than Excel. Still a great fit. Maybe we're a little disappointed in this first data point, but otherwise, we certainly seem to be capturing the trend of the data. So it's another tool that's handy to be aware of. We might be able to improve this with trial and error. You can certainly play around with it. Certainly a little tweak of the A is not helping any. Well, 0.56 is slightly better. 0.57 is worse. The other thing we could try to do is tweak our B. You could either change the number numerically or just change the fraction. So it changes to like 1 over 5.5. Notice that small change makes a dramatic difference, which shows how important your measurement is. So if you're a little bit off in your measurement, it's possible you'll get kind of a discouraging value, but notice you'll see that by not getting a good fit, and so then you can tweak your model accordingly. But we can certainly go back to where we were. So anyway, this looks like a nice fit, so we'll stop there. I encourage you to play around with it on your own and see if you can do even better. And that's it for this section. We'll see you in the next video.